This is our talk on a graph-based metadata model for DevOps in simulation-driven development and generation of DCP configurations. My name is Stefan Reiterer, and I also want to welcome my colleague Clemens Schiffer.
Hello.
In this talk, we will shortly start with the following contents. First, an introduction, then a short motivation. Then we will shortly dive into the theoretical background of our considerations. Then we will round this up with a simple use case description, and then we will talk about how we implemented this. And then we will final with a short conclusion. So we are from Virtual Vehicle. We are a small company, state-funded, and we have several stakeholders like Magna, AVL, Siemens, First Alpine, Infineon, and we also have a lot of partners which we work with and do projects from automotive, university, and rail. And we want to welcome you to come at us and make research project. We have good funding possibilities to make things happen, up to 100% funding. So there are a lot of possibilities. So come and talk about some project ideas with us. So, and now for our talk, let's start off with a some motivation. So on the one hand, we have, because it is needed for safety and to satisfy several processes like ASPICE, the classical redevelopment cycle in automotive. And this goes from product to system level, and of course to test and component level, and you are aware of. But on the other hand, we want to shorten time to market. And for this, we want to dive into agile processes and strategies as well, which are well established in software development already. But it's very hard in our V model world on the mechatronics side. So we have to talk about how to achieve this. And one cornerstone is DevOps, which consists of practices and tools to make continuous development happen. And we also have here, of course, to talk now about more, because DevOps is established in the software field, but still to make it more usable for our aspects, there is often more to do. And there is DevOps already happening a lot, but there is still room for improvement, especially to capture the complexity. And as we all know, especially how to deal with a lot of configurations, variant management, how to reuse existing components, and how also to store and version this in a proper way, especially versioning of different variants, concepts, etc., is especially hard. And for this, we have to talk about how to store it, how the proper data structure, and this will lead us to the co-simulation process graphs. So why graphs in the first place? First, graphs can express connections, we can model workflows, they are very flexible and versatile, and they can be stored in a graph database. And also it allows traceability because you just have to follow the graph inside the structure. So why are they relevant for us? Because they can represent architectures, represent car networks, and how everything is connected. So this gives us great possibility, not only for structuring things up, but also analysis on a large scale in the long run. This is the reason why graph models would be the thing to go. And also, if we go back now to DevOps and talk about pipelines. So pipelines describe CI processes, contain the scripts, and a lot of tools to make them happen and design them. But basically, every pipeline is a graph. To be more specific, a directed acyclic graph. For example, GitLab uses this concept because if you don't have a cycling in a directed graph, you can compute the topological order and then you get an execution order, and this can be done efficiently. And there are similar concepts explored already. For example, for original chemistry, there are process graphs, there are tool graphs, and from cloud area, there are also hybrid workflows. But for simulation, things are a little bit different because we would introduce now again cycles because of the simulation aspect. And so we have to talk about some rules to get back a directed acyclic graph, but still can represent simulations. So here a short example how this could look like. We have, for example, here two C functions and a build tool, which is deployed to build now a driving function, the sensor model, and then deploy in a simulation with the two FMUs and the DCP master. And then we have also feed in some configuration and play back some results. So, and here we would now give a simple use case to get a better idea what this entails. So Clemens, please.
So in our simple use case, we considered the typical roles involved in simulation development. The system engineer defines the system to be simulated, including the model boundaries, the scope, and the flow of the signals. The model developer implements the models based on the specified design, and the DevOps engineer provides pipelines for building and deploying the model components, and in our case, also for running the simulation. So in our use case, the models to be used are functional mockup units or FMUs. They are built using the FMU software development kit. And in these roles, the developer wrote the C code and the model descriptions that implements the models. This code is stored in a Git repository, and the DevOps engineer provides pipelines or templates for pipelines that are filled out and that are used to build these FMOs, to test them, and to deploy them to an artifact repository. Further built pipelines are used to deploy and run the simulation and then finally collect the results. Before we talk about the implementation, I think I should give a short introduction to the distributed co-simulation protocol. The distributed co-simulation protocol, or DCP for short, was designed to integrate models or real-time systems into simulation environments, and doing this independent of platform, architecture, or tool vendor. The DCP standard defines the configuration and data exchange of the simulation. DCP slave description in XML format that documents the capabilities as well as the inputs and outputs of each DCP slave have to be shared with the integrator before integrating the system. In our use case, we implemented a DCP master in Python. This highlights the interoperability of different implementations of the standard. This master is capable of reading in a scenario description, which contains a list of all the involved slaves, their slave descriptions, and how these in and outputs are to be connected. Also, DCP was designed with basic compatibility to FMI in mind. We used this by implementing a generic wrapper that makes existing FMUs available as DCP slaves. From the model descriptions of the FMUs, DCP slave descriptions are generated, and all inputs and outputs of the FMU can be configured using the DCP standard. All received data packages are set as inputs to the FMU, and outputs of the FMU are sent to the configured destinations as data packages. So our system that we want to simulate is the following. We want to test an adaptive cruise control or ACC function. This function calculates desired acceleration based on its inputs. The inputs are its own velocity or the velocity of the ego vehicle, also the distance and velocity of the vehicle ahead. And in our scenario, the vehicle ahead abruptly decelerates several times, as can be seen on the plot on the lower left, the speed 2, and on the lower right, you can see the reaction of the ACC function. That is, it decelerates each time the vehicle ahead brakes. The picture on the right shows the part of the graph that is related to the exchanged signals, and notes that this graph was dynamically generated from the UML data that serves as the input of the graph service. And the metadata of this graph, that is to say how the nodes are connected, that is used to generate the configuration that is given to the DCP master, which is used to deploy the simulation. For the deployment and running of the simulation, our simulations is deployed in Docker containers. So each participant, as well as the master, run in its own Docker containers, and these containers are connected with a Docker network. So first, the containers with the DCP slaves are started, and the DCP slaves start up and wait for the master. Then the Docker container with the master is started, and the master configures the slaves and starts the simulation. When the simulation is finished, all the results are automatically collected. Back to Stefan.
So now for the database side, so we have stored several pipelines beforehand. We have here also added one which is unrelated for demonstration purposes. And we have now the build pipelines for two components and the post-processing steps. So we now generate the description of the scenario of the simulation from the UML file, and then collect all the necessary data from the database, connect everything together, and then generate the code for the pipeline, which then results in our Jenkins pipeline, which is then executed and runs the simulation and stores the post-processing results. So to sum up, we have now showed the concept for graph-based metadata for simulations and pipelines. We demonstrated a prototype for FMU to DCP wrapper, and we made a proof of concept for automated CI pipeline generation from system description. As an outlook, we want to dive into more practical examples. We want to extend our example from the simple UML example to a real standard for simulations like SSP. And we also want to deal more with parameterization of models and variations. And then we also have to think about aspects of versioning security, especially DevSecOps. So here are some references to foregoing work. We also want to refer to our paper where we have more references. And thank you for your attention from me and Clemens.
Thank you.
Have a nice day.